Welcome back. We will be looking at the second derivative test for local extrema. So here's what we are looking for. So let's say that f has a critical point at c, where f prime of c is 0. If f prime of c is 0, that means that the slope of the tangent line to the graph of f at the point cf of c is going to be 0. In other words, the tangent line at the point cf of c will be a horizontal line. Now, when f prime of c is 0, there are three possibilities. Either at the point cf of c we have a local minimum, or at the point cf of c we have a local max. And there is a third possibility, which is that even though the derivative at c is 0, at the point cf of c is neither a local max nor a local mean. And notice that no matter how, notice that in every interval centered at c, there is an x value where the value of f is bigger than f of c, and there is an x value where the value of f is smaller than f of c. So this is neither a max nor a mean. The graph of x cubed is a prime example of that. So basically, when the derivative of f when the derivative of f at some c is 0, then we want to know whether at c we have a local max, mean, or neither, and the second derivative test will help us do that. So here's the second derivative test. So suppose that f prime of c is 0, so c is a critical point of f. Okay, so let me go back to the picture again. So how do I detect that f has a local minimum at c? Well, notice that if f prime of c is 0 and f has a local minimum there, that means that the graph of f is concave up at this point. So if I look at the second derivative of f at c, and if it is positive, then we know that f is concave up here, and so we have a local minimum there. When the second derivative of f at c is negative, then we know that the graph of f is concave down at this point, and so we have a local max there. So this is so if f double prime of c is positive, then f of c is a local minimum of f, and if f double prime of c is negative, that would mean that f is concave down at c, which would mean that f has a local max at c. If f double prime of c is 0, then we cannot apply this test. We have to figure out in other ways whether we have a local mix or min or neither at c. So for example, we could use the first derivative test to check whether at c we have a local max, mean, or neither in the third case. That is in the case when f double prime of c is 0. Here's an example. Let's say that f of x is x cubed minus 9x squared plus 24x minus 10, and we want to find the critical points of f, that is the points where the derivative is 0, and then we want to find the local max and local mean values of f. Okay, so the first thing we do is find the derivative, which is going to be 3x squared minus 18x plus 24. And notice that we can factor out the 3 here. That's going to give us x squared minus 6x plus 8. and this quadratic can be factored out into x minus 2 times x minus 4. So we see that f prime of x is 0 when either x is 2 or x is 4. So these are the two critical points of the function f. Now we want to know whether at each one of these critical points we have a local max or a local mean. So we're going to apply the second derivative test, and to do so we need the second derivative of the function. Now the second derivative would be the derivative of the first derivative, so we get 6x minus 18 as the second derivative of f at x is 6x minus 18. Now let's evaluate the second derivative at 2, and at 2 it'll be 12 minus 18, and that's negative. So because the second derivative at 2 is negative, that means that f is concave down at 2, which means that at 2 we have a local maximum. So f has a local maximum at 2, so f of 2 is 10. So 10 is the local maximum value. Let's calculate the second derivative at 4. At 4, it is going to be 4 times 6 minus 18, which is 24 minus 18, and that's positive. So f is concave up at 4, which would mean that f has a local minimum at 4. We see that f has a local minimum, and it also has a local maximum. And here's the graph of f. So recall that at 2, f of 2 was the local max, and f of 4 is a local minimum. Let's take f to be the function 10x to the 6 minus 24x to the 5 plus 15x to the 4. Again, we want to find the critical points and determine whether we have a local max or a min at each of the critical points. F prime of x is going to be 60x to the 5 minus 5 times 24, that's 120, x to the 4 plus 4 times 15, that's 60x cubed. First thing we need to do is factor out 60 and x cubed. If we do that, then we end up with so x to the 5. So when we factor out 60, we have to divide everything by 60. So from the first term we get 1, from the second term we're going to get 2, and from the third one we get 1 again. Now we are factoring out x cubed, so that means we have to multiply each term by x to the negative 3. So if I multiply this with x to the negative 3, we're going to get x to the 5 minus 3, which is 2. If we multiply this by x to the negative 3, we get x to the 1. Multiply this guy by x to the negative 3, we're going to get x to the 0, which is 1. So if we factor out 60x cubed, we end up with x squared minus 2x plus 1. Now x squared minus 2x plus 1 can be factored into x minus 1 squared. Okay, so we see that the derivative is 0 exactly when x is 0 or when x is 1. So we got two critical points. So this is the first derivative, and these are the critical points that we obtained in the previous slide. Now to apply the second derivative test, I need to find the second derivative of the function. And the second derivative of the function is 5 times 60, so that's 300x to the 4. 4 times 120, so that's 480x cubed. 3 times 60, so that's 180x squared. And we have to evaluate f double prime at 0 and 1. Now if we calculate f double prime of 0, we get 0, so the second derivative test is inconclusive. That is, the second derivative test doesn't tell me anything in this case. So we have to figure out whether we have a local max or mean or neither at 0 by using the first derivative test. But let's look at the second derivative at 1. Well, we're getting 0 as well. So the test fails for both critical points. And so we're gonna use the first derivative test. So we're going to, so these are the critical points, and they will be the partition numbers for the function f. So the domain of f would be all real numbers. We divide that at 0 and 1, and then we look at the sign graph for f prime. And notice that on the left side of 0, what's the sign of f prime? F prime of -1 is negative. So right here f prime, and we plug in -1 here, so we get -60, -120 here, and -60 here. So that's going to be -240, which is negative. So f prime is negative on the left side of 0. In between 0 and 1, we can pick half, and f prime of half. So it'll be, we have to plug in half in place of x here. And if we do that, we're going to get 1.875, which is positive. So in between 0 and 1, f prime is positive, and f prime of 2 is positive as well. So we get that f prime is negative, and then positive, and then positive. So we see that we see the following. So notice that right at 0, the function is, on the left of 0, the function is decreasing, and on the right of 0, the function is increasing. So right at 0, we have a local minimum. Now notice that at 1, the function is a continuous function, and it increases from 0 to 1, but then it keeps increasing from 1 to infinity. So we don't really have a local max or mean at 1. So f of 0 is the local minimum, and f has no local maximum. And let's look at the graph of this function. So this is how it looks like. So notice that on the left side of 0, the function is decreasing. On the right, right side of 0, the function is increasing. But notice what's happening at 1. Something interesting is happening here. So on the left side of 1, the function increases, and then right at 1, the slope becomes 0, but then it keeps increasing again. So this is the third case that I talked about here. Let me go back to the, so this is the third case right here, is what's happening at the critical point 1 here. Okay. Let me stop here.